Moving on to a Poisson process. If the events can occur at any given point in time or space, so they can occur, if the events can occur at any given temporal moment, or any spatial, or both together, we can model them as a Poisson process. Some examples of these would be an earthquake can occur at any given time. Stress cracks can occur anywhere along a beam. So there's a temporal example and a spatial example. We could model these as Bernoulli sequence. We can say, let's break our temporal space into, let's say, intervals of delta t. And then we can say within that delta t that an earthquake can happen or it cannot happen. There's a problem with that, though. If we make our Bernoulli sequence delta t interval too long or too short, as it could also be, then we may have multiple events occurring in our delta t. If we make them too long, that is. If we make them too long, we can have, let's say, 2 earthquakes occurring in some span. So modeling it as a Bernoulli sequence is not always the most appropriate way to look at things that can occur at any given point in time or space. Instead, we have the Poisson process. And the Poisson process has several rules. The event can occur randomly at any instant of time or any point in space. All right, so this right away. If it follows this, the event follows this, then our Bernoulli sequence is not very good at going to be able to predict how the probability associated with the events occurring or not occurring. The occurrences of an event in a given time or space interval is statistically independent of that in any other non-overlapping interval. So as with the Bernoulli sequence, the events are statistically independent of each other. The probability of occurrence of an event in a small interval delta t is proportional to delta t and can be given by what your book uses as nu delta t, where nu is the mean occurrence rate of the event. And this is always assumed constant. The probability of 2 or more occurrences in delta t is negligible. So we don't have that case of multiple events occurring within our specified delta t. If we follow all of these rules, then we have the basis for a Poisson process. And the PMF for Poisson process, and note that it's PMF, probability mass function, again, it is a discrete distribution, is given by this equation here in the center of the slide. The probability that our random variable x, and because it's temporal, let's say, let's call it x of t, is equal to some value x, is equal to nu t raised to the x divided by x factorial times the exponential of a minus nu t, where x can take on discrete values of 0, 1, 2, and so on. So x of t is the number of occurrences in time or space in some interval between 0 and t. This nu is the mean occurrence rate. So it's the average number of occurrences usually observed, sometimes predicted, but usually observed per some unit time or space. Now your book does a nice job of deriving the expected value of E sub t given this PMF, and it turns out that the mean number of occurrences in t is going to be equal to nu t. And the variance of our random variable x sub t is also nu t. Right, so this is easy to remember. The mean value or the expected value is nu t, and the variance of our x sub t in the Poisson process is also nu t. So in your text, I'm going to refer you to looking at on page 113. We have an example of 60 cars in making left-hand turns. And it states, from previous statistical data of traffic counts, an average of 60 cars per hour was observed to make left turns at a given intersection. Then suppose we are interested in the probability of exactly 10 cars making left turns at the intersection in a 10-minute interval. So before we get to the Poisson process of this, modeling this problem and answering the question, we want to look at a Bernoulli with varying delta t intervals. Ultimately, what we'll show is that as we decrease the delta t, we end up converging to a Poisson process. But we start with a Bernoulli sequence and a binomial distribution to answer this question. So let's start with what we have. We have 60 cars that were observed in 60 minutes to make left-hand turns. So this is what is observed. And we want to know how likely it is that 10 cars in 10 minutes make the turn. This is what we're after. So when we start with a Bernoulli sequence, let's make a coarse delta t. So the first delta t that we will look at is, let's say, 1 minute. That's our interval of time, 1 minute. So in 60 cars were observed in 60 minutes making turns. Delta t being 1 minute, in 60 minutes there's 60 intervals. All right, 1 minute, 1 interval. In 60 minutes we've got 60 intervals. So therefore, what this ratio shows us is the probability is equal to 100% probability that in the given interval a car will be making a turn. So to answer the question of how likely 10 cars, so we want the probability that x is equal to 10, modeled as a Bernoulli sequence and the distribution given to us by a binomial distribution. In 10 minutes, with a 1 minute interval, we've got 10 possible ways that we can make this happen, and x is equal to 10. So the number of trials is 10 because we've got delta t equals to 1 minute. We've got 10 minutes, so there's 10 intervals of this 1 minute in 10 minutes. So that's the number n. And then x, we want to know 10 in 10. And as you can probably predict right here, this is going to be equal to 100%. But let's go through the exercise anyways. So p is equal to 1, and we raise this to x, 10, and then we've got 1 minus p, which is 1 minus 1, raised to 10 minus 10, in this case n minus x, so it's 0, and this is equal to 100%. So now let's refine the resolution a little bit and make our delta t 30 seconds. So again, we need to figure out what is our probability for the individual event. So we've got 60 cars observed in 60 minutes, and in 60 minutes there is 120 30-second intervals. Right? Every 30 seconds is an interval, and in 60 minutes we get 120 intervals. So 60 cars in a 120-minute interval gives us our probability this time is 1/2 for this estimate. So again, we go with our binomial PMF, where x is equal again to 10. So we need the binomial coefficient. But this time we have 20 possible outcomes here. Our n is going to be equal to 20 because we have a 30-second interval. We want to find in 10 minutes how many possible intervals there are, total number of intervals. So that's going to be 20 intervals, and we want to find x10 in that 20. So that's where the binomial coefficient comes from in this case. So our p is 1/2. In this case, we raise it to 10, and then 1 minus p again is going to be 1/2, but raised to the 20 minus 10. So again, it's going to be 10. 20 n is 20. X is 10. to give us n minus x equal to 10. And this gives us a probability of 0.1762. And we're refining the resolution yet again, this time down to 10 seconds. So delta t is now 10 seconds. We have for our probability 60 cars in this time 360 intervals. 10 seconds in 60 minutes we saw 60 cars, and then there's 360 10-second intervals in 60 minutes. So this gives us our probability p equal to 0.1667. So the probability of seeing exactly 10 occur in 10 minutes, where x is equal to 10, is equal to our binomial coefficient, and this time in 10 minutes, in 10-second intervals, there are 60 of them, taking 10 at a time for our coefficient, and then we raise the p 1667 to our x10, and then 1 minus 0.1667, 60 minus 10 is 50, raised to the 50, gives us a probability of 0.1370. And finally, let's do a 1-second interval. So our delta t is equal to 1 second. So again, we have 60 cars. This time we have, in 60 minutes, we have 3,600 of these intervals, is equal to 1.67 times 10 to the minus 2 for our p. So our probability that x is equal to 10 is going to be equal to our binomial coefficient in 10 minutes, 1 second. So we have 600, 10, and then our probability 1.67 times 10 to the minus 2 raised to the 10 times 1 minus 1.67 times 10 to the minus 2 raised to 590, 60 minus 10. That gives us a probability of approximately 126. So if we look at all of the results and kind of put them together on a plot, let's say, where here we have the resulting probability of 10 cars, so x equal to 10, and then down here we put down the number of events that we systematically increased as we were making the estimate of the probability. We see that we started out as a certain event, 100%, so 1, and then as we increased, we went from all the way down. We went from 1 minute all the way down to 1 second, and we saw that we had a steady decrease, and then it started to flatten out. So we ended up, what the shape looks like is ultimately going to be converging to some asymptotic value. And as we'll see, this value is about 125. So as we continually refined our estimate of the delta t, as we decreased it, the probability that 10 vehicles making a turn in 10 minutes decreased to a flat value. We got to the end there, the last one was 126 when we did 1 second, and then 10 seconds it was 137. So we're getting out to this portion of the curve. And as we'll see, this actually converges to the what we call a Poisson process. So that example illustrates that when delta t gets smaller, we approach some asymptotic value. In other words, if we were to take the limit of the binomial as n goes to infinity, and your textbook goes through this derivation, what we would end up with is the PMF that was displayed a couple slides previously, where this is the PMF of this is the definition of the Poisson process. With they did a little swap of variables here. The textbook now uses lambda for this rate nu t, but this is the PMF of our Poisson process. It's nothing more than the limit as the number of occurrences that we are evaluating goes to infinity. So as we increase the n. So taking this to the extreme, that 60 car example, and now plugging it into our Poisson process, or modeling it as a Poisson process, we see that, well, our rate parameter, our nu, is the average number of occurrences during some unit, and it was observed that 60 cars make the turn in 60 minutes, so our rate parameter is 1 car per minute. So the probability that x is equal to 10, that we observe 10 cars making a left-hand turn in an interval of 10 minutes, is going to be our Poisson PMF, where we have our lambda, which is 1 car, which is our nu, times t. So we have 1 car per minute times 10 minutes. This is raised to the x, 10, divided by 10 factorial, x factorial, remember, times the exponential of minus lambda, which is nu t, 1 car per minute times 10 minutes. When we crank this out, we see that we get the limit of our Bernoulli sequence, and we end up with the Poisson prediction, modeling it as a Poisson process of 0.125. The Poisson process is very commonly used in civil engineering, in particular in traffic engineering. Some of you will go on to do senior design problems that include some type of traffic study. Remember this example in your traffic study when you get to that point, because this will be an effective way for you to get your hands around some type of probabilistic estimation associated with your senior design problem.